Hello, you're welcome. Okay, so now in this topic, we're going to be discussing the refraction of light. Okay, now remember, we've actually discussed the reflection of light. Okay, so we said that the reflection of light actually occurs once light encounters a boundary, okay, or a surface, then it is actually being thrown back to the medium. Okay, so that's for the reflection of light. And of course, those are the reflection, refraction, diffraction, polarization, interference. They are all properties or characteristics of wave. Okay, so now in this tutorial we're going to be looking at refraction of light. So let's start by defining refraction. Now refraction of light is the change in duration of light as it passes from one medium to another. Okay, and what causes that is actually due to the difference in the densities of the different mediums. All right, for example, air and let's say water medium, okay, they have different densities. Normally we are told that from the rectilinear propagation of light, that light travels in a straight line, and that is actually very true, possible when the light is moving through the same medium. Okay, but once light move from another medium to another, due to the difference in densities of the two mediums, definitely the ray of light will definitely change direction, and that is the refraction of light. Okay, so now this is this figure, the figure below shows refraction of light between air and glass. So as you can see, look at how that happens. Okay, all right, I'm going to draw this. Is actually, this diagram is for total internal reflection. Let me bring up a diagram that will actually illustrate the refraction of light. Okay, so give I will space out, right? Okay, here we go. All right, so okay, so now if I want to illustrate how refraction of light actually works, let's say I will create a medium. Let's say this is a glass or water. This is a different medium. Okay, then of course, for me to illustrate that, I need to draw a normal. Okay, any surface where refraction reflection will occur, you need to draw a normal to that surface. All right, so now let's say there's a ray of light, incident ray. Of course, you know that already when we discuss reflection. Okay, this is an incident ray. This light moves from air and hits this interface. Okay, this different medium. This medium here is air. Let's say this medium here is water, right? Or even glass. Okay, now I discovered that this light will no longer move, it will bend. Okay, so the bending of the light, as you can see here, is what is referred to as refraction. Okay, that change in direction. Now there's one thing you should know about refraction. Okay, whenever light actually undergo refraction, okay, something changes, because we know that for velocity of light, we have the velocity of light is given as wavelength times frequency. So, and of course we know that for the two medium, okay, the velocity differs. All right, so if light move from one medium to another, something changes. Okay, the velocity change. Okay, so let's say the velocity in air is v1, and of course in medium it will be v2. Another thing that will change also, the wavelength will also change. Okay, let's say wavelength in the air is lambda 1, and the wavelength in medium is lambda 2. Okay, but there's something that will never change. Please take note of that: the frequency. Okay, frequency of a wave remain the same irrespective of the medium is actually passing through. So please take note of that. So now we are going to look at the angle of incidence. This is the angle of incidence, right? The angle between the incidence and the normal. And of course, this is going to be the angle of refraction. Okay, between the refracted ray and the normal. Okay, so please take note of that. Okay, so we are going to look at a law, okay, known as Snell's law. That's what we're going to talk about now. We're going to talk about Snell's law. So here we go. So I bring it up to the screen. Okay, so this next law state that the ratio of sine of the incident ray to the sine of reflected ray in any medium is always constant. Okay, remember once refraction occur, okay, the ratio of sine of the incident ray to the sine of, please correct this, refracted ray, not reflected, because you're talking about refraction. Refracted, okay, so refracted, just correct that. Okay, so the ratio of the sine of the incident ray to the sine of the refracted ray in any medium is always constant, right? So according to Snell's law, the ratio of sine of incident, sine I, okay, sine I, then divided by sine R, incident and refraction, okay? The ratio of this sine I and sine R is always constant, and that constant is actually being given the symbol, okay, uh given the symbol of refractive index. Okay, so the constant is called refractive index. So which simply means that the refractive index of every medium, okay, is always given as sine I, all right, all over sine R. So please take note of that. All right, sine R. Now let's see example. So I have question here, okay, so we'll have to tackle, right? So let's do justice to this question. Okay, so here we go. Now I have the question goes like this. This is a diagram, okay, and of course this is the incident ray and this is the refracted ray, okay, which is now now um the incident ray, the angle of the incident is given as, it's not given, but rather the glancing angle. Remember, this glancing angle, this is actually the angle of incidence. So we simply means that the actual angle of incidence here is going to be 90, okay, 90 minus the glancing angle. So the angle of incidence is 60, okay, and the same thing happens with the angle of refraction, because for the refraction glancing angle is given, which is 60, so the angle of refraction here is 30, okay. So the question, if we are being asked to the refractive index of the medium, okay, so the refractive index of this medium is, of course, you know, that is sine of the incidence divided by the sine of the refraction, right? Okay, so from what I have evaluated, that the sine of this, the incidence is 60 degrees, right? The incidence is still 60 degrees, and of course the refraction is 30 degrees. Okay, so in this case you use special angle triangle. Special angle, okay, special angle, the sine of 60, sine 60 is root 3 over 2. Then divided by sine 30, okay, sine 30, the sine of 30 is half. Okay, so this is something as root 3 all over 2, right? Then times divided by, which of course we turn to reciprocal, 2 all over 1. So this cancel this. So the refractive index I'm looking for is the square root of 3, of course, which is 1.5, all right? So please take note of this, very important. Okay, so I proceed. Now we are going to look at another way of, okay, determining refractive index, okay. We're going to look at that, so I'll bring it up to the screen. Now refractive index, apart from being expressed in terms of the sine of the incidence, sine of the angle of incidence, and the that of refraction, refractive index can also be expressed in different way, okay, in different way. So this is another formula. Refractive index can also be expressed using the following formula. So refractive index can also be evaluated using the velocity of light in air divided by the velocity in that particular medium. So please take note of that, okay, velocity or velocity in that medium. Then refractive index also can be given as real depth all over apparent depth, real depth all over apparent depth. Now let me illustrate all this that I've just talked about now. Okay, let's say I have a glass prism. Okay, then if this ray should reach this particular medium, then of course it will refract. It will definitely undergo refraction, which will make it to bend. Okay, now on a normal, if this ray didn't refract, if I should trace it, okay, if I should trace it, this is exactly where the ray would have actually stopped. Okay, so the refraction actually make it to actually reach the depth. All right, so in this case now there are two depths. This depth, okay, of this medium, okay, is what is known as the real depth. Real depth, right? Now this depth that I trace, imaginary depth, okay, which of course if we assume that there was no refraction, okay, this depth from here to here, from this point to this point, assuming there was no refraction, this light should have moved in a straight line, okay, is what is known as apparent depth. Apparent depth. Apparent depth, okay. Excuse me. It's what is known as apparent depth. Let me get from here, please, from here to here. This is the, please follow me. It's from here to here, from the top to this point, okay. That's what is known as apparent depth. Let me use AP to represent it. Apparent, okay, apparent AD. All right, so another way of expressing refractive index is refractive index can be given as the real depth, okay, real depth of a medium divided by the apparent depth. Okay, so from the top of the medium to the point, this point here, okay, without considering refraction, is the apparent depth, while from the top of the medium to the actual depth of the medium is the real depth, okay. So now there's a displacement between this apparent depth to the real depth. That's a small displacement here. There's a difference between the real depth and the apparent depth, okay, and that is the displacement depth. And how do I get that displacement? Okay, so the displacement, anytime refraction occurs in a particular medium, all right, to get the displacement, you subtract the real depth RD minus the apparent depth AD. Real depth minus the apparent depth. Okay, so please take note of that. I think that explains a whole lot of things. Okay, let's see if we still get some question to evaluate. Okay, now let's look at, I'm gonna just bring some question down. Right, so okay, I'll just put question on the screen so that we'll evaluate it. Okay, a container, a container, container, okay, a container of water of depth of depth 2 meter. Okay, has refractive index, refractive index, has a refractive index of 1.33, 1.33. 0.03. Okay. Evaluate. Evaluate. Okay. Evaluate its displacement. Okay. Evaluate the displacement of ray of light. Ray of light. Ray of light. Incidented. Incidented. Incidented on it. All right, so let's walk. Okay, so we're gonna walk. We are gonna solve this question. So now I have solution. Now, before I can actually get the displacement, I need to get the apparent depth. Okay, so refractive index is always equal to real depth, right? All over the apparent depth. Okay, so refractive index is 1.33. And the real depth of that container is 2 meters. So the apparent depth, I don't know what it is. Okay, so I have to rearrange the equation. Okay, so I have apparent depth. Okay, apparent depth is gonna be equal to 2 divided by 1.33. All right, so what do we have? Let's get a calculator. Okay, so I have 2 divided by 1.33. Okay, so that gives me 1.5 approximately. Okay, don't forget the displacement. Okay, the displacement. So displacement of the ray of light, okay, is simply going to be evaluated using the real depth RD minus the apparent depth AD. So this is going to be equal to the real depth is 2 minus the apparent depth, which is 1.5. Okay, so that gives us 0.5. So that's the displacement. The displacement is 0.5 meter. All right, so let's proceed. So here now we're going to discuss total internal reflection of light. Okay, I'll bring it up to the screen. Okay, here we go. Total internal reflection. Now, total internal reflection actually occurs, okay, when angle of incidence exceeds the critical angle of a median. Okay, now I will explain this. Okay, you know very well that if we incident a ray, okay, at the interface of two medium, it will refract. Okay, this is already known. Okay, it will refract. All right, now from the formula of refractive index, which we know that is sin I, okay, all over sin R. If I should actually cross multiply, I can simply say that, okay, sin I, sin of incidence, okay, is equal to refractive index multiplied by sine of refraction. Okay, now from this particular relationship, we can simply say that incidence is directly proportional to refraction. Okay, that simply means that when the incidence increases, the refraction increases. Okay, so let's come to this place now. That means if I keep on increasing the incidence of this particular of this medium, okay, the refraction will increase. If I increase it again, the refraction will increase. Okay, if I keep on increasing the incidence, the refraction will increase. Okay, so there's going to be an increment to a point where the refraction will now tends to come, okay, becomes perpendicular to the surface. Okay, all right. Now at that particular point, you will simply know that the incidence have actually reached what is known as the critical angle, because once this refraction has actually reached the surface, if you increase the incidence any longer, there won't be any refraction again, because this ray of light now have left the medium. Okay, it will now come out outside the medium, it becomes a refracted ray. Okay, so that is what is known, and that is when total internal reflection occurs. So that is why total internal reflection is said to occur, okay, when the angle of incidence actually exceeds the critical angle. So let's go back to that particular note now so that you understand it. Okay, this occurs when the angle of incidence exceeds the critical angle of a medium. Then the ray will reflect instead of refracting. So if that exceeds, then there's going to be a reflection, no more refraction again. Okay, now at that particular point, okay, where we say that the angle of incidence, okay, exceeds the critical angle. So we can simply say that critical angle is the angle of incidence, okay, when the angle of refraction is 90 degrees, perpendicular is 90 degrees, okay. So please take note of that. Okay, the critical angle of a medium is actually the angle of incidence, okay, that will make the angle of refraction to be what? To be 90 degrees. Okay, so please take note. So we now go straight to the formula. How do we actually derive formula of refractive index whenever total internal reflection occurs? I will probably do that. Okay, so now please take note of the condition. Okay, first of all, for total internal reflection to occur, the angle of incidence must exceed the critical angle of that medium. All right, that's number one. And the ones that have on the, okay, the light will actually reflect. Okay, and that thing you need to understand, total internal reflection occur when light actually moves from a dense medium to a less dense medium, because at that particular instance now, when total internal reflection occurs, okay, light is now moving from, okay, light is now moving from this medium, from the dense medium to a less dense medium. Okay, so that means light is now moving from, let's say if it is glass, okay, it is now reflecting glass to air. Okay, so please take note of that. Now let's go straight to the formula, which is very important. Okay, now the formula of refractive index, we know that refractive index is equal to sine I all over sine r, right? Okay, so refractive index is I all over sine r, and we simply know that, okay, well, considering light, okay, in the case, okay, in this case, light is actually moving, okay, at that point, the angle of incidence, okay, is actually 90 degrees. That's critical angle. So we can simply say that, okay, refractive index is equal to sine 90, right? And of course, the angle of refraction is the critical angle, okay, is equal to sine c. All right, so at that point, sine 90, if you do sine 90, you're gonna have 1, of course, and of course divided by sine c. All right, so that is why for a total internal reflection that occurs, we will have, okay, refractive index equal to 1 all over sine c, while c is the critical angle. Okay, in case you are being asked to evaluate the critical angle, but let's actually look at um, let's look at question that will illustrate this. Okay, I think this is an example. Okay, example: a ray of light is situated on a glass boundary at an angle theta. If the angle between the partial reflected ray and the refracted ray is 90 degrees, calculate theta. Okay, so this is 90 degrees. This 90 degrees is the angle of uh, uh, reflection. Okay, the angle of refraction, sorry. Okay, and of course the angle of incidence at this point where the angle of refraction is 90 degrees is the critical angle. So from the formula, refractive index at that point is given as 1 all over sine c. Please take note. Okay, sine c, and that c, okay, becomes the critical angle, and according to them, calculate the c. The c here, they call it theta. Okay, so that is going to be 1 all over sine theta. 1 all over sine theta, right? Please take note of that. So putting the value according to the question, the refractive index is 1.5. So I'm going to have 1.5 divided by 1 all over sine theta. So if I actually want to get sine theta, all I just need to do is I'll find the reciprocal of sine theta, right? So I will invert it. That will be sine theta now. If I invert it, I also have to invert this. That will be 1 all over 1.5. Okay, if I do 1 over 1.5, I have 0.667. Okay, so sine theta is 0.67. So theta now is going to be equal to sine inverse of 0.67. So how do you do sine inverse? You just do shift. Okay, shift sine inverse, right? Cool. Do we have that here? Okay, so I'm looking at the sine inverse if everything is calculated. So just use your calculator, do the sine inverse of this. Okay, so you get the answer. All right, so let's actually proceed so that we will conclude this topic, right? Okay, of course, sine inverse of 0.67, that's 41.80, so you can confirm that. So now let's actually look at the application of total internal reflection. Okay, let's look at the application of total internal reflection. All right, so I bring it up to the screen. Alright, so application of total internal reflection is found in the following. Okay, it's found in mirage, formation of mirage, fish eye view, and optical fiber. So let's start. I'm going to describe them one after the other. Mirage is actually an optical illusion. Okay, the word mirage is an optical illusion. An illusion is something that makes things that is not real looks like real. Okay, it is not really, but it looks like real. So that optical illusion is an illusion that make you, when you're walking on a third road, okay, you actually look ahead of you in a car. It seems as if there's a pool of water ahead of you, but as you go close to the pool of water, it seems as if it's receding, okay, it's moving away from you, okay. So that is an optical illusion, and that optical illusion is actually caused by total internal reflection, because the ray of light, okay, from the sun before it passes, as moved from the sun, okay, as it goes, it passes different densities of air. Because of that movement of different densities of air, it will actually undergo total internal reflection, okay, which will cause some image to be cast at a particular level, at particular position known as apparent position. Remember, apparent position is not really the real position, okay? So that will give you an illusion of apparent images being at a particular point. And of course, because it has to do with ray of light, as that apparent image that is formed by an apparent ray, as you go close to it, okay, because you are the observer, okay, it's relative to your eyes, okay. It will always give the distance relative to your eyes, so it will always go further from you, okay. And as you go close, it's not real, okay. So it's only an image. It's like a kind of shadow, okay, that was formed, but it's formed due to total internal reflection. Then, of course, let's discuss about the fish eye view. Fish has the ability of seeing every almost a wide distance, okay, above the water surface. Is that sharp. The fish is that sharp to see everything. The reason being that the rays of light from the eyes of the fish, once it reaches the surface of the water, it totally internally reflected, okay. Because of that total internal reflection, it expands. The rays expands, okay, at the surface, giving it a wider eye view. Then now have optical fiber. Optical fiber is made up of a pipe, okay, a pipe of glass that can actually bend, okay. But one thing about the pipe of glass is that when light enters into it, it will be totally internally reflected. There's going to be multiple total internal reflection, okay, that can actually cause it to be for you to use it to see across uh, uh, see in a round corner, okay. So with an optical fiber, you can actually put it inside a hole, okay, and see the inside of any particular building that you want to see, because no matter how much you bend it, once light rays enters into the optical fiber, it will undergo multiple total internal reflection that will actually bring the image of wherever it is actually located, okay, to the person that is viewing it, okay. So you can do research on all those things about optical fiber, okay. Now, okay, this is a question. State two factors which affect the angle of deviation of a ray of light through the triangular prism, okay. So this is a question that one get to tackle. All right, I think we'll talk about angle of deviation. We're going to look at triangular prism, okay. Refraction in a triangular prism, that will be what we're going to be looking at in our next video, okay. Triangular prism, and triangular and rectangular prism, we are going to look at how refraction occurs in those two types of prism, okay. So see you in the next video. Thank you very much.